This episode is brought to you by Cisco Educational Premium.
The atom is the basic building block of matter around us. Your body, your clothing, your chair, your bed, even the device you're watching this video on is made of atoms. The idea of the atom is basically the reason why chemistry exists. The periodic table of elements is basically built on atoms. Ever since the idea of the existence of atoms was put forward by the philosopher Democritus, who said that the universe is made of atoms and the void in which they exist. This idea was since given a solid grounding by scientists, particularly chemists and physicists, proving its existence by scientific method. Today, there is solid evidence that atoms exist, and when we say that atoms exist, we really do know what we are talking about. An atom is most efficient as a dense and compact nucleus encircled by rapidly moving orbiting electrons. This concept naturally raises the question: how do electrons sustain their motion around the nucleus without slowing down? This question became a major concern in the early 20th century and led to the development of quantum mechanics itself. During this time, physicists were making strides in understanding atoms and recognized that each atom contained a positively charged nucleus with a considerable mass surrounded by tiny negatively charged electrons. Armed with this general understanding, they sought to construct a more detailed model. Initially, scientists drew inspiration from the solar system with a dense nucleus, the sun orbited by smaller particles, the planets. However, this model posed two significant issues. First, charged particles that accelerate must emit electromagnetic radiation by observations and at least by Maxwell's equations. Since electrons are charged and accelerate during their orbits, they should emit radiation which will cause them to lose energy and quickly spiral inward into the nucleus. However, atoms are known to exist far much longer than a picosecond, making this model incorrect. Secondly, atoms were observed to emit radiation at specific frequency, unlike the continuous emission expected from an electron following the solar system model. Niels Bohr, a renowned Danish physicist, was the first to propose a solution to these problems. In 1913, he suggested that electrons in an atom do not just occupy just any orbit but confined to specific distances from the nucleus. He also proposed that there was a minimum distance an electron could reach beyond which it could not move any closer to the nucleus. Bohr's ideas were not just mere speculations. They were built on the work of German physicist Max Planck, who had proposed the quantization of radiation emission a little over a decade. According to Planck, objects could only absorb or emit radiation in discrete chunks, not in any arbitrary value. These discrete chunks were characterized by constant value known as Planck's constant, which had units akin to angular momentum. Bohr adopted this concept and applied it to electrons orbiting a nucleus. He asserted that the smallest possible orbit of an electron will have an angular momentum equivalent to 1 Planck constant. Higher orbits would have integer multiples of the Planck's constant, such as twice or 3 times its value, but never fractions like half or 2 and 3. The full comprehension of why electrons possessed specific orbits and well-defined energy levels required the more complete development of quantum mechanics. Electrons, like other matter particles, exhibit both particle and wave behavior. While we might envision an electron as a tiny planet orbiting the nucleus, we can usually visualize it as a wave enveloping a nucleus. Waves confined within a limited space must adhere to specific rules. They cannot have arbitrary wavelengths. Instead, they must consist of standing waves that fit precisely within the space. This is analogous to playing a musical instrument. When you fix the ends of a guitar string, only specific wavelengths produce distinct notes. Similarly, the electron wave circling a nucleus must fit the available space, and the nearest orbit is determined by fast standing wave of that electron. Future advances in quantum mechanics would continue refining this model, but the fundamental point remains unchanged. An electron cannot approach the nucleus any closer due to its inherent quantum mechanical constraints, which prevent it from occupying smaller space. However, an entirely different approach to understand this situation does not rely on quantum mechanics at all. Instead, it considers the various energies involved. An electron in orbit around the nucleus experiences electrical attraction towards the nucleus, constantly being pulled closer. At the same time, it possesses kinetic energy trying to propel it away from the nucleus. For a stable atom, these two forces are in equilibrium. In fact, the total energy of an electron in orbit, which combines its potential and kinetic energies, is negative. Consequently, adding energy to the atom is necessary to remove an electron. This concept parallels the behavior of planets orbiting the Sun. To remove the planet from the solar system, energy must be added to the system. One way to envision this scenario is to picture an electron falling inwards towards the nucleus due to the attractive electric charge. However, because of the principle of quantum mechanics, the electron can never reach the nucleus, becoming perpetually in a stable orbit. Nevertheless, this situation is permissible according to physics because the total energy of the system is negative, signifying its stability and binding components together to form a long-lasting atom. Everything around us is composed of atoms. All the matter in the observable universe is estimated to be more than 10 quadrillion quintillion. This number is 1 followed by 78 zeros. Atoms are tiny particles consisting of electrons, protons and neutrons, which are in turn made up of quarks. The origin of these particles that make up atoms can be traced to the Big Bang. The Big Bang theory explains the beginning of the universe, where an immense amount of energy condensed, leading to the formation of atoms. There are more technical details than this, which we are going to look at them. To understand the scientific perspective of the Big Bang, we need to examine the events of the early universe. Unfortunately, we do not have a definitive understanding of precisely when the universe started, or if it indeed started at all. Our base model, the standard model of cosmology, allows us to trace back time close to the beginning, but we encounter a barrier at t is equal to 1. This theory predicts a singularity, a moment of infinite density where all matter and energy were compressed into an infinitely small point. Most physicists predict that this prediction may not be entirely accurate. We can only go back to 1 Planck time, which is about 10 raised to negative 43 seconds. Before this, we have no knowledge of what occurred both by observation and mathematics. So while we get very close to the beginning, it is not precisely at t is equal to 1. Understanding the events of this incredibly small time scale requires a quantum theory of gravity, where gravity, which explains the behavior of large objects, meets quantum mechanics, which governs the behavior of particles at tiny scales. The epoch of the universe, known as the Planck epoch, occurred at 10 raised to negative 43 seconds. During this time, it is believed that all the fundamental forces, including electromagnetism, the weak force, the strong force, were unified as one grand unified force at this point. However, it is important to note that this isn't exactly t is equal to 1, as we want to avoid the singularity. The state of the universe at this epoch and what happened before it remain unknown. The earliest time we can theorize about is the period of inflation, which occurred from about 10 raised to negative 36 seconds to about 10 raised to negative 33 seconds after the Big Bang. During this time, whatever existed prior to inflation experienced rapid exponential expansion, faster than the speed of light. This is allowed because there is no theoretical restriction on the speed at which space itself can expand. It expanded from a point to a point about the size of a baseball. You might wonder how this is even possible, since we know that nothing can travel faster than the speed of light. While this is true for information transfer, cosmic inflation involves the expansion of space itself, allowing distant points to move away from each other faster than light can travel between them. Most of our current understanding comes from the period after inflation. So the accurate way to view the Big Bang is not as a single point of origin, but as a period when the early universe was extremely hot, dense, and rapidly expanding. Thus, the Big Bang is a description of everything that occurred after t is equal to 1. Inflation is believed to have occurred from 10 raised to negative 36 to 10 raised to negative 3 seconds. The energy source behind this rapid expansion and cosmic inflation erased any information about what existed before it. The theory of the standard model of cosmology is well understood, starting at about 10 raised to negative 12 seconds, as the universe's energy levels can be reproduced in current particle accelerators. Before this time, we can only speculate about the events. From about 10 raised to negative 3 seconds to 10 raised to 12 seconds, strong force and electromagnetic and weak forces, collectively known as electroweak force, was still unified. The origin of the initial massless fundamental particles is uncertain. They might have condensed from the energies present during the Big Bang, or an inflation field containing inflations could have decayed into the fundamental particles we observe today. Around 10 raised to negative 11 seconds, the temperature drops further to 10 raised to 15 Kelvin, marking the beginning of the quark epoch. The electromagnetic and weak forces begin to separate, leading to electroweak symmetry breaking. The X fields gains a non-zero potential, imparting mass to the fundamental particles of the standard model. At this point, the essential components of atoms are in place, and the universe temperature is around 1 quadrillion Kelvin. As the universe continues to expand and cool, the extremely high temperatures present prevent quarks from combining into hadrons like protons and neutrons. However, as temperature drops to about 1 trillion Kelvin at 10 raised to negative 5 seconds, the quark plasma transitions into a hadron gas consisting of protons neutrons, and certain mesons, which eventually decay into photons and electrons. As the temperature further decreases, particles and antiparticles begin to annihilate, resulting in lighter particle-antiparticle pairs, such as neutrinos and photons. Interestingly, there is a slight asymmetry in this process, which with more particles being generated than antiparticles, leading to the survival of certain quarks and electrons. This enables the formation of protons, neutrons, and electrons, which are essential for creating the initial atoms. The annihilation process culminates with the Lipton epoch, which occurs around 1 second mark when the temperature subsides to about 5 billion Kelvin. During this epoch, leptons conclude the annihilation process. Following this remarkable display, the majority of the matter particles transforms into photons and neutrinos. However, due to the matter-antimatter asymmetry, a small quantity of protons, neutrons, and electrons remain surviving as the fundamental building blocks for atoms. At around a few minutes after the universe's inception, the epoch of the Big Bang nucleosynthesis (BBN) begins with protons and neutrons produced in equal numbers. Free neutrons are inherently unstable and undergo beta decay, transforming into protons over approximately 10 raised to 50 minutes. As the temperature remains high, proton-neutron conversion is balanced by neutron-proton conversion. But as the universe cools further, neutron decay becomes more prevalent. Free neutrons strive to join other hadrons and form more extensive nuclei before decay, leading to the universe consisting of about 75% hydrogen nuclei and 25% helium-4 nuclei, along with small amounts of deuterium, helium-3, and trace quantities of lithium-9 nuclei. In this period, the environment predominantly consisting of ionized nuclei without bound electrons. The formation of neutral atoms requires electrons to attach to positively charged nucleons to achieve charge balance. However, the universe is still scorching and electrons can only briefly adhere to nucleons before being forcibly separated due to their immense energy. As a result, the universe remains opaque and photons carrying light continuously interact with nucleons and electrons, hindering their free propagation through space. This photon epoch lasts for about 380,000 years until the universe cools down to 3000 Kelvin. At this point, electrons possess significantly reduced energy, allowing the electromagnetic force to permanently bind them to nucleons, leading to the formation of stable neutral atoms in a process called recombination. As a consequence, photons are no longer confined amidst the chaos of positive nucleons and negative electrons. They are now free to traverse the universe. If an observer was present in space, he or she would be able to observe this light. Today, the first light of the universe, known as the cosmic microwave background (CMB), can be perceived in all directions. This light was emitted during the formation of fast stable neutral atoms, providing us with valuable insights into the early universe and the origin of atoms. Atoms constantly interact. However, to comprehend this, we must first determine the definition of interact. Our typical understanding of interaction is based on the macroscopic world. I place my palm on the chair. My palm interacts with the chair. You step on the floor, you interact with the floor, and so forth. In these instances, one solid boundary or surface interact with another solid boundary or surface. Nevertheless, our macroscopic understanding becomes less applicable at a microscopic level, which lead to confusion about interaction. If we could magnify the scale to atomic level, we would witness a chaotic environment. Atoms and molecules are consistently in motion, colliding, twisting, and spinning, resulting in a chaotic scenario. However, one thing becomes evident: atoms lack a definite boundary. They exist a nucleus, a collection of protons and neutrons at the center, surrounded by clouds of probabilities that indicate the potential locations of orbiting electrons. The principles of quantum mechanics allows us to calculate probabilities which extend through the entire universe. Nevertheless, in nearly all observations, electrons remain securely bounded to the nucleus. So unless we are conducting high energy collider experiments, we don't have to worry too much about it. Since atoms lack a firm surface in a way, there's no tangible touch because there is never a direct meeting of the boundaries. However, touch also implies close and influential interaction, and in that sense, atoms are in constant contact. Atoms interact due to the electromagnetic force which arises from the electric charges of the protons and electrons within them. Technically, this force has an infinite range, but it becomes significant only when atoms are significantly close. At times, atoms literally repel each other due to the electromagnetic force between their electrons. In that brief movement, it is challenging to describe their interaction as anything but touching. Even if the interaction is not momentarily, it still qualifies as touching. For instance, when we examine the palm at the chair at the atomic and molecular level, we notice that the electrons at the palm outer edge are repelled by the electrons on the chair's outer edge. Despite the gap within the layers of electrons which typically exist, the atoms are close enough to significantly influence each other. This is evident from the fact that the cup does not fall through the chair, and the electromagnetic forces between the atom counteract the gravity's pull of the cup. At the macroscopic scale, when we say two objects are touching, it reflects the same interaction at the microscopic level. Atoms can also touch through other means. As electromagnetic force is not always repulsive, when atoms get close, the van der Waals force, the manifestation of the electromagnetic force, can lead to bonding between atoms. This process results in the formation of molecules, where the atoms inside them are definitely in contact. Lastly, even nuclei within atoms can touch, although it is extremely difficult due to the strong electromagnetic repulsion between the positively charged protons in each nucleus. Yet quantum mechanics play a role here too. If two atoms are brought close enough and maintained for sufficient time, occasionally and randomly, their nuclei can intermingle. This phenomenon leads to nuclear fusion, where two separate atoms merge into a single larger atom. If the atoms involved are lighter than iron, the fusion process releases energy. It is through this mechanism that all stars, including our sun, generate their power. Two atoms of the same element are typically non-indistinguishable. First, electrons in an atom can occupy a range of possible states. Therefore, two atoms of the same element can be different if their electrons occupy different states. For example, one copper atom with an electron in an excited state and another copper atom with all electrons in the ground state are distinct. The excited copper atom will emit light when the electron returns to the ground state, while the copper atom in the ground state will not. The nature of the chemical bonding experienced by an atom depends on the state of its electrons. So two atoms of the same element can react differently if they are in different states. We chemists are aware of this fact, and to fully describe and predict a reaction, it is necessary to specify excitation states of the electrons in the atoms. Additionally, even when left alone, an atom often does not have an equal number of protons and electrons. However, even if two atoms of the same element have their electrons in the same state, they are still not identical. For example, they could be traveling or rotating at different speeds, which influences their ability to chemically bond. Slow moving atoms, such as those in solid iron, have time to form stable bonds, whereas faster moving atoms, like those in liquid iron, cannot establish such stable bonds. As a result, a slow moving thin atom is different from a rapid moving thin atom. But what if two atoms of the same element both have their electrons in the same state, and the atoms are both traveling and rotating at the same speed? Then are they indistinguishable? No. Although two such atoms are essentially chemically identical, they will chemically react in the same way. They are chemically identical. Beyond the electrons, there is also the nucleus to consider. An atom's nucleus contains tightly bonded neutrons and protons. The same chemical element can have different number of neutrons and still be the same element. This atom with different number of neutrons are referred to as isotopes. While a particular isotope involved does not impact an atom's chemical reactions, it does determine how an atom behaves in nuclear reactions. Radioactive decay, the most common nuclear reaction on Earth, varies among different isotopes. Some isotopes decay rapidly into other elements and emit radiation, while others do not. For carbon dating, the fact that carbon-12 is not the same as carbon-14 atom is crucial to the dating process. Simply counting the number of carbon atoms in a sample will not provide information about the sample's age. Instead, you have to count the number of different isotopes of carbon. But what if two atoms are of the same element, have electrons in the same state, and traveling and rotating at the same speed, and have the same number of neutrons? Then are they indistinguishable? No. Just like electrons, the neutrons and protons in the nucleus can exist in the various excited states. Additionally, the nucleus as a whole can rotate and vibrate at different speeds. And even if all else is identical, two gold atoms can have their nuclei at different excited states and behaves differently in nuclear reactions. In summary, achieving two atoms of the same element to be perfectly identical is exceedingly difficult. In fact, such an accomplishment will be a Nobel Prize worthy. Nevertheless, it is important to note that atoms do not possess individual identities beyond what has been mentioned here. If two carbon atoms are in the exact same molecular, atomic, electronic, and nuclear state, then those two carbon atoms are identical regardless of their origin or past history. Everything has color. Since almost everything have color, atoms as the fundamental building blocks of reality should also have color. Or does it? When you aggregate numerous atoms together, you obtain the screen that you are constantly observing, which indeed has color. So, does it imply that each individual atom has its own color as well? If so, is it the nucleus or electrons that are painted? And if so, what color? The color we perceive are a creation of the human brain. They don't actually exist outside our visual perception. So then, what precisely is color? To understand this, we need to comprehend the nature of light. Light consists of photons, which are particles. However, This behavior is only evident when observed. Otherwise, they tend to act as electromagnetic waves. This phenomenon is known as the wave-particle duality concept. And yes, it is peculiar. These waves possess specific frequencies, and depending on their frequencies, they are classified to 7 primary wavelength sections, ranging from radio waves with wavelengths the size of Earth to gamma rays the size of atoms. The human eye can only perceive only a small section of the visible light, while everything else becomes invisible. And come to think of it, why are we only sensitive to visible light? Why this particular region is significant? It's because the first eyes evolved while organisms inhabited underwater environments. This portion of light is transparent in water. Infrared and ultraviolet light, however, renders water somewhat opaque. If the first organisms evolved in sulfur lakes orbiting a neutron star, their eyes might see something like X-rays. How does light form, and how does it enable us to perceive color? In the core of the sun, hydrogen nuclei undergo nuclear fusion due to immense pressure, transforming into alpha particles and emitting gamma radiation. This radiation ricochets around the sun, colliding with other hydrogen atoms over thousands of years, using energy in the process, and ultimately emerges as visible or ultraviolet light. It then reaches Earth. Light can either be absorbed or reflected depending on the material it encounters. This is determined by the nature of material. For example, a blue piece of cloth appears blue because it reflects the blue wavelength of light while absorbing all other wavelengths. Thus, it is every color but blue, since blue is reflected and not absorbed. This is why black materials heat up significantly in the sun. They absorb all light and reflect very little. On the other hand, the opposite is true for white. All of this is referred to as bulk absorption and reflection. When a beam of light interacts with many atoms simultaneously, fact is such as the distance between molecules or how the molecules are organized may affect the colors of light reflected. For instance, snow and ice are both composed of same type of molecules. However, their different arrangement result in snow being white and ice being transparent. Meanwhile, water absorbs minimal light and most of it passes through. One will need to venture deep into the ocean to avoid seeing sunlight. Similarly, consider carbon organizing its atom in a lattice results in diamonds, while arranging them in hexagon produces graphite. So coming back to our initial question, do atoms possess color? From the perspective of bulk reflection, no. The wavelength of light are larger than the size of an individual atom. Thus, color only becomes apparent at larger level. But what about thermal radiation? When you heat something up, the atoms inside start to vigorously collide with each other, releasing photons. Regardless of the substance type, the emitted light will adhere to the same color spectrum. However, once again, this only applies when you have more than one particle. For individual atoms, no color can arise from thermal radiation. Finally, there is gas discharge. By passing electricity through a cloud of atoms, they become excited and release photons. The emission of photons in this scenario can vary in wavelength, resulting in different colors depending on the substance nature. As a result, each element possesses each emission spectrum. These are the colors emitted by hydrogen atoms, and similar patterns exist for atoms and other elements. In conclusion, each chemical element has its distinct color fingerprint defined by its emission spectrum. In a sense, you could consider that as its color. However, in a literal sense, the one we perceive in our everyday life? No. An atom is physically smaller than the wavelength of light, making color non-existent at the atomic level. There are four fundamental forces or interactions in nature: gravity, the weak force, electromagnetism, and the strong force. Gravity is most familiar to us at larger scales, but at the quantum level, the other forces dominate. Electromagnetism is exceptionally stronger than gravity, approximately 10 raised to 37 times, and is responsible for electron-proton attraction in atoms. The question arises, why don't multiple protons in the atomic nuclei repel each other strongly due to electromagnetism? According to Coulomb's law, in a helium atom, the two protons experience a repulsive force of about 90 newtons or 20 pounds, which should cause them to fly apart instantly. However, the reason protons remain bound is the presence of even stronger force called the strong nuclear force. The strong nuclear force is about 100 times stronger than electromagnetism. It operates at the scale of atomic nuclei. This force works differently from electromagnetism, and I know it might be new to most of us. I only came across when I took some of nuclear science courses in college. The fascinating world of quantum chromodynamics reveals how protons and neutrons stay tightly bound within atomic nuclei, resisting the enormous repulsive force of electromagnetism. The strong nuclear force, which is responsible for the binding energy within atomic nuclei, accounts for about 99% of the mass of ordinary objects. This is contrary to the misconception that Higgs field is the primary contributor. To understand the strong force, we need to explore the composition of protons and neutrons. They are made up of quarks, fundamental matter particles, and gluon, force particles. A proton contains 2 up quarks and 1 down quark. Neutron, on the other hand, contain 2 down quarks and 1 up quark. Gluons responsible for keeping quarks together carry a color charge. This is analogous to an electric charge, but function differently and is unrelated to optical colors. The color charge comes in 3 types: red, green, and blue, which combine to make a neutral white. Color charges need to be balanced to create neutral charges, either through a combination of the 3 colors or through color anti-color charges. Gluons interact with quarks and bind them together. Quarks and gluons are the only particles affected by a strong force. Gluons serve as the force mediators, similar to photons in electromagnetic interactions. If quarks get too close far apart, the rubber band breaks, but instead of releasing the quarks, the energy required creates a new quark-anti-quark pair called a meson. This confinement principle ensures that free quarks cannot exist, and they are always confined within at least one other quark. Mesons play a crucial role in interaction between protons and neutrons in the nucleus. While the strong nuclear force is weaker than the strong force between the nucleons, it is still much stronger than the electromagnetic repulsion between positively charged protons. This force only acts at very short distances around the diameter of a proton and diminishes rapidly with greater distances, limiting the size of stable atomic nuclei. In summary, the strong nuclear force mediated by mesons keeps protons and neutrons tightly bound together in the atomic nuclei. It works in harmony with a strong force that binds quarks within nucleons. This understanding of the strong force is essential for comprehending the nature of matter and the existence of objects and life as we know it. The visible universe is mainly composed of fewer than 100 naturally occurring elements. Nevertheless, this limited set of building blocks, called atoms, give rise to an astonishingly diversity of chemical substances, both in the cosmos and within our own body. The reason for this vast array of chemical substances is that atoms rarely exist in isolation. Instead, they predominantly combine with other atoms through chemical bonding, creating an almost limitless array of chemical components and materials. These combinations give rise not only to the multitude of phenomena observed in the universe, but also to the complexity necessary for life, energy sources, consciousness, and other macroscopic processes. The universe is not monotonous because atoms form bonds with each other, resulting in rich chemicals with properties fundamentally different from their constituent atoms. This happens because of the role that energy plays in the formation of molecules rooted in quantum mechanics. Important chemicals in our lives, such as the air we breathe, are composed of molecules rather than individual atoms. Oxygen, for instance, exists as the atomic molecule with two oxygen atoms bound together. Similarly, nitrogen is found as a diatomic molecule, and water is H2O, consisting of two hydrogen atoms and one oxygen atom. Atoms predominantly exist as molecules due to their tendency to adopt a state of lowest energy. Just as a marble at the top of the hill will naturally roll down to bottom, all natural systems seek to minimize their potential energy. This principle also explains the unidirectional flow of river from high ground to lower ground. Energy plays a crucial role in the formation of molecules. For instance, when looking at the simplest atom, hydrogen, consisting of one proton and one electron, it is usually found as H2 or hydrogen gas. Quantum mechanics explain how atoms form molecules to achieve lower energy states. When a second hydrogen atom is introduced, interesting interactions occur. As the atom gets closer, the electrons, being negatively charged, repel each other, but they also get affected by the positive charge in the other atom, leading to attraction. There's a balance or sweet spot distance where the protons prefer to be allowing electrons to be shared while minimizing repulsion. The attraction between the atoms is not solely through electronic cloud repulsion. Multiple interactions are at the play. The system's behavior is governed by the total energy of the system, determining how atoms bond together to form molecules. To determine the lowest energy state of a two-atom system, such as an hydrogen molecule, several factors must be considered. Kinetic energy of each atom and the potential energy between the protons and electrons. These calculations are encapsulated by the Hamiltonian, representing the energy of the system in quantum mechanics. Solving the time-independent Schrödinger equation using the Hamiltonian yields possible values for energy. However, this equation is not easily solvable and is often represented graphically, showing the energy changes as the two atoms move closer together. At a certain point, the graph exhibits a dip, representing the lowest energy state when the atoms are at an optimal distance from each other. In this optimal state, the two atoms are more content being together at a lower energy level than they were separately. This is why hydrogen atom naturally combine to form molecules of H2 rather than remain isolated. Such electron sharing between atoms is known as a covalent bond, and similar covalent bonds form between other atoms. The stability of atoms and their tendency to bind with others are related to the number of electrons in their shells around the nucleus. Atoms with specific numbers of electrons such as 2, 10, 18, 36, 54, or 86 are particularly stable due to the lowest potential energy they possess. These numbers correspond to the electron count of the naturally occurring noble gases, which are chemically inert and do not bind with other atoms. Atoms strive to attain a full valence shell electrons, which involves either sharing of electrons through covalent bonds or transferring electrons through ionic bonds. The attractive force for sharing electrons to achieve a full valence shell is balanced by the repulsive forces between electron clouds and electrons. The explanation for this magical number lies in quantum mechanics, specifically in the Schrödinger equation and the Pauli exclusion principle. The latter states that no two fermions, such as electrons, can occupy the same quantum state, and electrons in same orbitals must have opposite spin. By combining these principles, these specific sequences of numbers are determined as the ones resulting in the lowest potential energy of chemical systems. In complex calculations involving many atoms like in water, approximations like the most potential equation are commonly used. These calculations show bond lengths that leads the lowest potential energy of the molecule. Ultimately, quantum mechanics helps us to understand how nature behaves, but it doesn't provide the underlying reason on why nature is as it is. It merely illuminates the working of nature without explaining the fundamental why. Neutron stars are some of the extreme entities found in the universe. They appear as colossal atomic nuclei with diameter stretching over kilometers and possessing mind-blowing density and violence. But how can such a phenomenon possibly exist? The existence of a star is intricately balanced between its gravitation force and radiation pressure stemming from fusion reaction at its core. Within a star's core, hydrogen undergoes fusion and transforms into helium. As time passes, the hydrogen supply depletes, and if the star is massive enough, helium begins fusing into carbon. As these massive stars evolve, their cores undergo layering with progressively heavy atomic nuclei accumulating at the center. Carbon further fuses to neon, which further transforms into oxygen and silicon. Ultimately, the fusion process reaches iron, an element that cannot undergo further fusion. When the fusion process halts, the radiation pressure diminishes rapidly, causing the star to lose its equilibrium. If the core mass exceeds about 1 to 4 solar masses, a catastrophic collapse ensues. The other part of the core accelerates with velocities reaching up to 70,000 kilometers per second as it collapses inwards towards the star's center. At this point, all the fundamental forces operating within an atom come into play to counteract gravitational collapse. The quantum mechanical repulsion between electrons is overpowered, leading to electrons and protons to merge into tightly packed neutrons. The other layers of the stars are finally expelled into space during a supernova explosion. Now we witness the emersion of a neutron star. Its mass varies between 1 and 3 times that of our Sun, compressed into a compact object with a diameter of approximately 25 kilometers. It contains the equivalent mass of about 500,000 Earths, akin to the size of Nairobi. The neutron star density is so extreme that 1 cubic centimeter of its material holds the same mass as an iron cube spanning 700 meters across. That explains why the Hawk can not lift Mjolnir. Sorry guys, just think aloud. Sci-fi. This quantity amounts to roughly 1 billion ton, comparable to Mount Everest mass, confined within the space of a sugar cube. The gravitational pull of a neutron star is remarkably potent as well. Dropping an object from 1 meter above its surface would cause it to hit the star in 1 microsecond and accelerate to velocity of 7.2 million kilometers per hour. The surface of a neutron star displays an exceptional flatness, with irregularities not surpassing 5 millimeters. It possesses an extremely thin atmosphere of hot plasma. The neutron star surface reaches approximately 1 million Kelvin, contrasting with our star temperature of 5,800 Kelvin. The crust is incredibly solid and likely composed of ion atom nuclei lattice and dispersed with a sea of electrons. As we approach the core, the number of neutrons increase while protons decrease, eventually resulting in an immense mixture of indistinguishable neutrons. The core of neutron stars remains enigmatic and mysterious. Although we haven't fully grasped their properties, the prevailing belief suggests that they may be composed of superfluid neutron degenerate matter or an ultra-dense quark matter called quark-gluon plasma. These peculiar states of matter defy conventional understanding and can only thrive in ultra-extreme environments. In many aspects, a neutron star bears resemblance to a colossal atomic nucleus, distinguished mainly by the forces binding them together. Atomic cores are governed by strong interaction, while neutron stars are governed by gravity. If it weren't already extreme enough, let's explore some other attributes. Neutron star exhibits incredible fast rotation, with young ones spinning several times per second. If a nearby star is unfortunate enough to be captured by neutron star gravitational pull, it can accelerate its rotation to several hundred times per second. As in the case of PSR J1748244-6D, which spins at an approximately 252 million kilometers per hour. This rapid rotation leads to a peculiar star-shaped. We designate these objects as pulsars due to their emission of strong radio signals. Additionally, the magnetic field of a neutron star is approximately 8 trillion times stronger than Earth's magnetic field. This magnetic force is so potent that it bends the path of atoms as they come under its influence. The observable universe, with its vastness, is hard to grasp, and according to certain theories, it may be relatively insignificant. Current calculations indicate that the unobservable universe could even be larger, possibly exceeding 20 trillion light years in diameter. Despite its enormity, much of it might be empty, similar to the scarcity of observable universe. Matter composed of countless atoms is incredibly small, beyond the resolutions of our most advanced microscopes. Scientific evidence confirms the existence of atoms consisting of subatomic particles like protons, neutrons, electrons, and quarks. Astonishingly, there are theories suggesting that everything, including humans and entire observable and unobservable universe, could be akin to an atom in a grand reality. One such concept is a one-electron universe theory, suggesting that what we perceive as multiple electrons might stem from just one particle moving swiftly back and forth in time, creating the illusion of many. Speed mirage. Thinking loudly again. Although this theory lacks scientific support, It serves as a starting point for other similar ideas with more backing. A more mainstream variation is rooted in the multiverse theory, proposing that all atoms, electrons, and properties of matter in our universe could be equivalent to an atom in a larger universe. This idea has been explored in science fiction, where our universe is seen as a mere speck in a higher plane of existence, or where each atom within us contains all other existences. Infinity plays a vital role in these concepts, suggesting that no matter how vast our universe is, if the multiverse theory holds, there could be infinitely larger universes, making us appear subatomic from their perspective. Observing the universe, we see how tiny subatomic universes come together to form increasingly larger structures from celestial objects to complex organisms. This leads to the question on whether the universe itself could be part of something greater. The blurring of micro and macro levels cannot be disregarded until we have a comprehensive theory of everything. This will unify quantum and classical physics. According to the popular theory of the universe creation, it began as an infinitely dense singularity before expanding through the Big Bang, implying that everything we know was once inconceivably small. However, it is important to note that the initial singularity contained the necessary components for the formation of atoms, distinguishing it from an actual atom. Although these ideas challenge our understanding of reality, they serve as thought experiments to contemplate our place in the vast cosmos. While they might be mind boggling, they do not diminish the wonder and significance of our existence. String theory is considered one of the most leading contenders for the theory of everything, aiming to understand the true nature of reality. In this theory, atoms are not depicted as spherical objects, but rather as string-like structures that vibrate, responsible for all interactions of the universe, including the laws of physics, gravity, and quantum mechanics. However, string theory faces challenges, particularly concerning dark energy, which constitute a significant portion of the universe. Most string theory models struggle to explain the dominance of dark energy compared to observable universe and compared to observable matter. Some recent attempts have been made to incorporate the dark matter into string theory. These include variations proposed by researchers from Uppsala University in Sweden. This variation suggests that our universe exists on an edge of constantly expanding bubble where everything we know is merely a small component of something much larger. Inside the bubble and beyond its edge, a known dimension might exist, and the infiltration of dark energy from the wider bubble universe could provide a better explanation. If this version of reality was accurate, it would drastically change our current understanding of science. It would place human beings as infinite small parts within a much larger, grander, and incomprehensible structure. However, it is essential to recognize that this idea is merely a thought experiment, a fun way to ponder our place in the cosmos. Even if our perspective prove limited and our knowledge flawed, the insignificance from another viewpoint does not necessarily diminish the value of our existence.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So, do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.
Yeah.